Okay, kids, we're back. Section 4.4, section question 2. At the moment when a shot putter releases a 7.26 kilogram shot. So the shot is the ball that they're going to throw. That's what a shot putter throws. 7.26 kilograms. All right. The shot is 2 meters above the ground. So let's draw that. Here's the ground. Here's the shot putter, right? And the shot putter is going to be holding the ball, okay? And when the ball is being thrown, the ball has a height of 2 meters. Notice these are not vectors, right? So that's where the ball is, 2 meters, and is traveling at 15 meters per second. So that's the velocity there, 15.0 meters per second. It reaches a maximum height of 8 meters above the ground. So the shot put gets thrown into the air, right? And then it's going to reach a certain maximum height right there, okay? So when the shot put is right there, its height is 8 meters. So we can't have two H's. So we have to distinguish here, right? So let's call this height initial, and let's call this height final. Is that okay? All right. And then it falls to the ground. Assume the air resistance is negligible. What is the gravitational potential energy of the shot as it leaves the hand relative to the ground? So, required gravitational potential energy here. Right here is the initial. That's the initial. So that's height initial. We can even call this speed initial. That's the initial situation. So we're going to call this gravitational potential energy initial. You see how I added an I there? It's gravitational potential energy initial, right? Analysis. Gravitational potential energy initial is the mass of the object, the magnitude of the gravitational field strength. You notice it's not a vector here. The magnitude of the gravitational field strength multiplied by height initial. So we're going to substitute, and this would be 7.26 kilograms, 9.8 newtons per kilogram. Notice there's no negative sign. This is just the magnitude part. Height of 2 meters. So I get my handy dandy fancy dancy calculator out, and I type in 7.26 for the mass times 9.8 for the magnitude of the gravitational field strength times 2 for the height, and I get 142.3. The gravitational field strength initial is 142.3 joules. Is that okay? Okay, so now we're moving on to B. Is this correct? Okay, B. In part B here, the required, they want us to find the kinetic energy as the ball, the shot, leaves the hand. So we want to find the kinetic energy. Look here, initial, right? It's still the initial situation as it leaves the hand. So analysis, kinetic energy initial is equal to half the mass of the object times its speed initial squared. That's the equation. I hope you remember that. Notice it's speed squared, not velocity squared. This is all scalar. Okay? So now we're going to substitute. And we have kinetic energy initial equals a half times the mass of 7.26 kilograms, and the speed as it left the hand was 15.0 meters per second, and we square it. So it's 0.5 times 7.26 times 15 squared, and we get 816.8. That's the kinetic energy initial. So far, so good? Okay, so that's B. All right, now C. C. Let me extend the page here. There we go. So for C, the required for C is, what's the total mechanical energy there? Well, required energy total. Energy total where? In the initial situation. Analysis. Energy total initial is equal to gravitational potential energy initial plus kinetic energy initial. That's the definition of gravitation, excuse me, of total mechanical energy. So now we're going to substitute. And the total gravitational potential energy was 142.3. All scalars here, 142.3 joules, plus the kinetic energy, 816.8 joules. Finally, the solution. Total energy initial, I have to add these up. And basically we get 959 joules. 959 joules. So that's C, the total mechanical energy. Where am I talking about here, kids? Right here. Right here, just as it leaves the hand. Just as it leaves the hand. That's C. D, what is the total mechanical energy of the shot as it reaches its maximum height? Well, what's the total energy here? We're ignoring air resistance. Okay, well, let's talk about that. So this is D. And the required for D is total energy in the final situation, right? The second place. Analysis. Well, one of the things that they're teaching you in this section right here is the law of conservation of energy. And the law of conservation of energy says you can't get rid of energy and you can't create it. So whatever energy you start with, you will have later on. So what it's telling you is that the total energy final equals the total energy initial. It does not change. That's the law of conservation of energy. So we're going to substitute and solution at the same time here. Total energy final is the same, 959 joules. Doesn't change. It does not change. Next. E, what is the gravitational potential energy of the shot at the maximum height? So required. Gravitational potential energy in the final. Okay, what am I talking about here? I'm talking about it's been thrown into the air and it's right here somewhere. How much gravitational potential energy does it have there? Well, okay. Analysis, gravitational potential energy final is equal to the mass of the object, the magnitude of the gravitational field strength near the surface of the Earth, times height final. Now we're going to substitute, and we get gravitational potential energy final is equal to the mass of the shot which is 7.26 kilograms, times the magnitude of the gravitational field strength near the surface of the Earth, 9.8 newtons per kilogram, times the height final, which is 8 meters above the ground. Notice this is all scalar. There are no vectors here. So now I get my handy-dandy, fancy-dancy calculator out because it's supercalifragilisticexpialidocious. And I'm going to multiply 7.26 times 9.8 times 8. And we get basically 569. So that is the gravitational potential energy of the shot when it's at the 8 meters in the air. Any questions on that? No? Okay. So that is E. So we have to continue. We have to continue. F. What is the kinetic energy of the shot at its maximum height? So F. Required. What is the kinetic energy of this shot, this ball, when it's at that 8-meter height? So you would probably like to think, oh, okay, I know the equation for that. I know the equation for that. It's half the mass times the speed there squared, right? Isn't that the equation? There's a problem, though. You don't know that. You literally don't know that. So since you don't know that, you can't use that equation. You have to use another equation. And let me show you what it would be. It would be total energy final equals kinetic energy final plus gravitational potential energy final. So I'm using the definition of total mechanical energy. Total mechanical energy at any position is equal to the sum of the kinetic energy at that position plus the gravitational potential energy at that position. All right? So I want to find the kinetic energy. So I rearrange this equation and I get kinetic energy final is equal to total energy final minus gravitational potential energy final. So kids, all I did to find this is I brought gravitational potential energy to the other side of the equation and it became negative. That's all I did. So now we want to substitute. Kinetic energy final is equal to total energy final, which is the same everywhere. Where's that? Where's the total energy? There it is, 959. So I put it in. Minus the gravitational potential energy final. And we calculated that right here. See? 569. So I go 959 minus 569, all in joules, and I'm left with a solution of kinetic energy final is equal to 390 joules. So that was part F. What is the kinetic energy of the shot at the maximum height? So what is the kinetic energy of the shot? What is the kinetic energy of the shot just as it strikes the ground? Just as it strikes the ground. So this is a little bit different. So let's go back to our drawing. Here, the object, look, it started here, it went to the maximum height, and then it hits the ground. So when it hits the ground, let's call this height final, right? Height final, it's zero height, okay? And we want to find what's its kinetic energy when it just hits the ground. Okay, so let's do that. So this is G. And G, we want to find the kinetic energy as it just hits the ground. So let's call it kinetic energy final. Okay? That's our required analysis. We need to find an equation that will allow us to calculate this. We can't use half the mass times the speed squared. We don't know the speed when it hits the ground. We have no idea. So we have to use this equation right here. Total energy equals kinetic energy final plus gravitational potential energy final. Now, do we know the total energy? Yes, we do. It never ever changes. It's the law of conservation of energy. It never changes. So we know that. Do we know the kinetic energy final? Well, no, but that's what we want to calculate. Do we know the gravitational potential energy when it's at the ground? Actually, we do. Because we know the height there. So the gravitational potential energy when it's at the ground, well, at the ground, the height is 0. It has no height at the ground. So if you multiply anything by 0, you get 0. I don't care what the gravitational field strength is. I don't care what the mass is. I'm multiplying it by 0. So that means the gravitational potential energy final is 0 joules. Nothing. It's at the ground. It has no height. If it has no height, it has no gravitational potential energy. So that means this whole thing is gone. It's 0. So this equation just becomes total energy is equal to kinetic energy final. Well, do I know what the total energy is? Yes, I do. It never ever changes, and it's 959. So it's really substitution and solution at the same time. 959 joules is the kinetic energy final, right when it's hitting the ground. So this really takes advantage of the law of conservation of energy. So that's G. H. Apply the law of conservation of energy to determine the final speed of the shot. How fast is it moving when it hits the ground? So required velocity final. Speed final. I got to be careful. It's speed final. So analysis. Is there an equation in this energy method that has speed in it? Yes, there is. Kinetic energy final is half the mass times the speed final squared. Aha! Can I calculate this? Yes, you can. All you have to do is rearrange this equation. So you multiply both sides by 2. So it becomes 2 kinetic energy final. A half times 2 leaves me with 1. So I don't even write them 1 down. I multiply both sides by 2. Okay? Now I'm going to divide both sides by m. The m's cancel. And I'm left with 2 times kinetic energy final divided by mass is equal to speed final squared. And now I'm going to substitute. 2 times kinetic energy final. How much is it? I don't want to go back on my screen. How much is it? Kinetic energy final. Did you write it down? Well, it's the same as total energy. 959. 959 joules. Divided by the mass of the shot, 7.26 kilograms. equals velocity, speed final squared. So I get my handy dandy fancy dancy calculator out. 2 times 959 joules equals, divided by 7.26 equals, but then I have to realize that if I want the speed final, I have to square root. So I'm going to square root that, and I get 16.2, 16.3 meters per second is equal to the final speed as it just hits the ground. So we've done it, and it took us 21 minutes. I had fun. I hope you did. Okay, I'm going to record this now. Bye.